Okay, we're live. Welcome everyone to the 6th Tuva Community Meetup. Super excited today for this one. We've got Coco and Brad presenting on risk-adjusted benchmarking. And I'll hand it over to them in just 1 second, but I wanted to just share a little bit about why I'm so excited for this. Coco and I first started building risk-adjusted machine learning models to do risk-adjusted benchmarking. I think it was was it 2016 at Health Catalyst?
Coco? Yeah, 16.
Yeah. And I had used risk adjustment from other vendors going back to my days at Colorado Medicaid. And it's just such an important tool for analytics, because the point of analytics a lot of the time is identifying where we're performing well or not performing well. And so then that always brings in the question, well, compared to what? And with your patient population changing all the time, you need to do risk adjustment. And to have a comparison to something that's fair, you need to do risk adjustment. And so this was kind of our whole, the reason Coco and I started the Tuva Project is because we were like, look, there's all these different tools that you need to be able to do healthcare analytics, and we just don't have access to all of them. Most healthcare data teams have access to some of them, but then we end up kind of struggling through the rest or reinventing the wheel and on the rest. And so I think this is such an important one. And so what we've done is we purchased, we got access to Medicare fee-for-service claims data, the limited data set standard analytic files, which is a 5% national sample of all Medicare fee-for-service members and their associated claims. And then we use that to train these models. And it's the same data we used when we were at Health Catalyst almost 10 years ago now. But just, I guess not exactly the same data. It's not from 2016. It's much more recent. But anyways, I'll shut up because we've got an exciting presentation. I'll hand it over to Coco and Brad, but I'm personally really excited for this one. So Coco, Brad, take it away.
Cool. Let me share and start going. Can everybody see this?
Yep.
So I can't see you now, and I can't see the chat. So in the spirit of all the community meetups that we do, we try to keep it pretty informal and just have an open conversation. So please feel free to interrupt with any questions that you have. And I'll start by saying I think there's two main goals that we want to get from this presentation. So the first goal being, we really want to give a good overview of how we think about doing risk-adjusted benchmarks. Like Aaron was saying, Aaron, myself, Brad, other people on our team have spent quite a bit of time doing this in the past, and we've seen different ways of doing it. There's better and worse ways to do it. What we're presenting today is a pretty standard approach that's considered best practice in the industry. And so we'll walk through what that looks like. The second main goal for today is to dive more deeply into the specific models that we're open sourcing and showing you the inner workings of how they were trained and how you can use those models on your own data to generate risk-adjusted benchmarks. So let's just jump right in and start talking about how we think about doing risk-adjusted benchmarking. So we can start by asking, what is benchmarking in the first place? In simple terms, benchmarking is just about comparing performance against some standard. So why would you want to do that? Because it allows you to see how you're doing, right? So if you're doing really well or really badly or just as expected, you would find that out by comparing to something. And doing this comparison in a smart way, that is what the art of benchmarking is all about. So we'll spend a few minutes just talking about what that looks like and how you can do this comparison in a smart way. So imagine you have a population of patients and you want to ask any question about these patients. So for example, you want to ask, what is the spend for this population? So you can report a number, say $17 billion. Obviously, this number by itself is completely meaningless because was the spend for 1,000 patients? Was the spend for 100 million patients? But let's say you know the number of patients, say 1.5 million patients. Reporting a number like $17 billion for this many patients is still completely meaningless. Was it spent for a year? Was it spent for 10 years? You don't know. So obviously answers to these questions determine whether the metric that you're looking at is very high or very low or just as expected. And here's where the concept of PMPM comes in hand. I know many of you are familiar with the PMPM. It stands for per member per month. And it's completely customary in healthcare data analytics to report any metric of interest normalized in a per member per month basis because people have intuition about what that means. So for example, if you're talking about spend PMPM, what you mean is that you're looking at a time period of interest and you're looking at the total dollar spend in your population in that time period of interest, and you're dividing that by the total number of months of enrollment across all your members in that same time period of interest. So if you have these two numbers, if you have the total spend, the total number of months of enrollment, you can calculate your spend per member per month. And so this number now, you can report it as saying my medical spend PMPM is $911, for example. And so this is meaningful, right? People have intuition about what PMPM means. This is not just some free-floating figure in the void with no context. We know what our spend is per member per month. But then if you ask a question like, is this spend high or low? That's a different question. And to answer this question, you need to compare that to something, and that's where benchmarking comes into play. So if you compute any metric of interest in your patient population, like for example, medical spend PMPM, you need to have a benchmarking population that you can compare against. And this, for example, could be a national claims data set that you've acquired for this purpose. And you compute the metric of interest in both populations, and now you can compare that, right? But the natural question to ask is, how do you know that this is an apples to apples comparison? Because obviously your population could be older or sicker than the benchmarking population. Maybe even if the metric you're computing is slightly higher on your population than on the benchmarking population, maybe you're still doing really well given how sick your population was in the first place in comparison to the benchmarking population. So a workaround to make sure you're doing an apples to apples comparison is to compare very uniform subsets of your population with similar subsets in the benchmarking population. So for example, you could look at people over 65 years old in your population, and you compute a metric of interest in those people and compare with the benchmarking population. Similarly for people under 65, but why not get more granular? Obviously people over 65 in both populations could be very different. So you can try to define a more uniform subset and say, for example, let's look at females between 60 and 65 with type 2 diabetes, compute a metric of interest in this cohort in both populations and compare that. And then obviously you could just keep asking why stop there. Those people could also be very different. So let's say you look at females between 60 and 65 that have type 2 diabetes, that have hypertension, ESRD, a social vulnerability index of greater than 0.9, and you can get to a very uniform cohort, compare a metric like in that cohort for both populations. But you can see where I'm going now, right? If you just say, why not take this approach to the limit? And if you're going to more and more narrow cohorts that are more and more uniform, and you take that approach to the limit, you basically arrive at a cohort of one single person. And so then you're asking for this specific patient's comorbidities and demographic information and social determinants of health and medical history, et cetera, what is their expected spend in a given time period? And I'm using spend as an example, but you can ask, what is their expected X for any metric of interest, given their personal characteristics? And so now you can train a model to predict spend or whatever metric of interest for each individual patient in your population. And so you can look at patient number one, you can look at their personal features, and the model predicts what their spend should be. Patient number two, you look at their personal features, the model predicts what their spend should be. And you do this for every patient in the population. The model predicts whatever metric of interest is for each patient one at a time, considering what they look like as a person. And so if you want to look at, for example, the expected spend for your entire population, what you do is that you predict it for each patient individually, and then you add that all up to compute the total spend for the full population. So here's an example of a spend that's normalized PMPM that's calculated using predictions from a model for your entire population. And so now you can compare that to the actual medical spend that you've seen on your population, and you can see how you're doing. The model that's trained to do this is trained on a large benchmarking population. So the model learned average trends based on a wide variety of patient features. And therefore, the model can make accurate individual predictions for any one of your patients. So even if your population looks very different, the same model can be used on a very different looking population. And it doesn't matter how the population looks as a whole, because the model is making predictions on each individual patient based on their personal features. So somebody was recently asking me, can I use the models that you're open sourcing on my population if they look, it looks very different or they're sicker? And the answer is absolutely yes. You're just making predictions on each patient one at a time. So this whole thing that we've been talking about, when you have the two populations and you have to worry about whether you're comparing in an apples to apples way, and you're trying to figure out how to create uniform cohorts so that the comparison is actually meaningful and apples to apples, all of this is now completely unnecessary because you have this one model, and the model can be used against any patient population, whether it looks like this or like that. So this approach you can use to benchmark any metric of interest because you have the flexibility of training a model to predict whatever metric you want. So whether it's a spend metric, a utilization metric, for example, if you're trying to predict spend or benchmark spend, you train a model that predicts spend per patient per year, but you could also train a model that predicts acute inpatient spend or emergency department spend or whatever metric you're trying to benchmark per patient per year or per time frame that makes sense for you. And similarly for utilization, you can train a model that predicts the number of ED visits that each patient is going to have each year, or the number of acute inpatient stays that each person is going to have each year. So you have that flexibility to benchmark whatever you want by training models for that. An important caveat that I want to mention is that when you train a model on a benchmarking population, you train a model to predict whatever metric of interest, but one of the key ideas when doing risk-adjusted benchmarking is that your goal is not pure predictive power. You're not trying to make the model that makes the most accurate predictions possible. The goal is, in fact, to make causally fair estimates of what should have been expected, independently of the provider or of their utilization patterns. So the question that you're trying to answer is, how did this provider or system perform given the risk profile of their patients? And you're making patient-level predictions, and each patient-level prediction is answering the question, what would be a reasonable or typical spend for this person, regardless of where they received care? So obviously, you could choose to include in your model things like the identities of your providers or the local utilization patterns, known behavior of that provider group, or are they high spenders? Do they typically have aggressive treatment styles? So if you include these kinds of things in your model, the model is going to have more predictive power. It's going to be more accurate. But by doing that, you're baking in the effect that you're measuring into the model. So that would be analogous to trying to evaluate how a teacher is performing by trying to predict the test scores on standardized tests of their students. And the model that you use to do that takes into account that teacher's past performance or their students' performance on tests. If the teacher is really bad, their students historically have performed horribly on tests. If you take that into account, you would be predicting that their current students are going to do really bad. And when you compare what you predict with what happened, it's very close. So you could conclude that the students are doing just as expected, but in fact, they're doing really bad. So you don't want to bake that behavior you're trying to measure into the model. So what you want in your models is you want features that reflect patient-level risk, things like the demographics of the patients, their diagnoses, comorbidities, medical burden of each patient. It's okay to include regional level effects if geography can impact cost, but you want to avoid provider level signals. So you avoid this problem. And so if you take this into account, you're creating a fair baseline and you're predicting what you would expect for these patients independently of who treated them. And so the key thing to remember when making models for risk-adjusted benchmarks is that it's always possible to train models with higher predictive power than the ones you want to use for risk-adjusted benchmarks. But that's not what you want. You don't want the maximum predictive power. You just want a fair estimate of what would have happened, what is expected for those patients. So to summarize, you need two main things to do risk-adjusted benchmarking. The first thing that you need is a sound methodology. So this is what I've been talking about, having risk adjustment best practices, knowing what features are good to include and what are not good to include, knowing what grain to train a model in for the specific thing you're trying to benchmark. You want to have data science knowledge and skills so that you can train a model, make sure you're not overfitting the model, make sure you can evaluate the performance of the model, make sure you can engineer features that are appropriate. You need ML ops chops so that you can put the models that you trained into production and generate risk-adjusted benchmarks on your own data. All of this is what we're open sourcing today. We're open sourcing the knowledge of how to do it in the code for how to train the models. But this is no secret sauce. Like Aaron was saying, we've done this multiple times in the past as part of different teams. This is just best practices in the industry. This has been published in many places in papers and books. We particularly like this book that we followed in our approach. by Ian Duncan. It's if there anybody who's interested in the detailed theory of how to do risk-adjusted benchmarking, this is a really good reference. So that's one thing that you need, all this methodology and knowledge to do this. Another main ingredient of what you need is data for benchmarking. And so in this case, we need data to train the models in. So like Aaron said, we bought the CMS LDS data set, we trained models on this data set, and that's unfortunately, we can't make the full data set available to the world because that would be in violation of our contract. But what we can do is that we can train models on that data set, so the models learn behaviors and can make predictions on your data, and we can make those models available for anybody to inspect and use. So these are the two things that we're making available in open sourcing today. So now I want to change gears a little bit and just walk you through an example of how you would create just one model, just to give you a sense of the kinds of things that you have to think about when you create a single model for risk-adjusted benchmarks. So I'm going to use as an example,
Hey, Coco,
creating a,
we did have a few questions come in before you dive into the next section. I don't know if you want to tackle those or if you wanted to wait till the end.
Yeah, let's do it.
So we had Naren ask if the benchmarking population is restricted to just Medicare patients. And for these initial models that we're releasing, these are just trained on the LDS data set that Coco has mentioned. But I believe we do have plans to release other models in the future.
Yeah, I can add on to that, Brad. We're getting access to third-party data for commercial and Medicaid lines of business as well. Unfortunately, we won't be able to open source those models just because of the data use agreements that we'll have with those, with whoever we get the data from. That data is also quite a bit more expensive. To give you a sense, you can buy a year of Medicare LDS data. You have to go through an approval process. There has to be a research use case. And so you can't just get access to the data for anything, but you can get access to Medicare LDS data 1 year for $17,500. Getting access to commercial and Medicaid data. I mean, there's a few different options, but you're talking on the order of like kind of 250, 500K, something along those lines. So we won't be able to open source those models, and then financially it would probably be tough to open source those models as well. But we are making them available as part of paid offerings. So that's what I would add to that.
All right. And
cool.
then,
Is there another question?
One more question from JD, where he asks how much historical data is usually needed, and if historical data is an anomaly from periods like 2020, how would we handle that?
Yeah, that's a good question. You can, we're not training, we have 2020 data, but the models that we're releasing are not trained on that. So we chose to train it. What is it, Brad? Is 2023 data?
Yeah, we're using 2022 and 2023 data for these models that we're releasing.
Yeah. But yeah, that's a good point to take into account. That if you have a data set that is very unusual, like 2020, of course you have to be careful and not train models on that for predicting on a normal year.
And I think 2024 LDS data comes out next month, and so we'll buy that data at that time and release new models.
Yeah.
And then we just got another question from Spencer, who asks if any comparisons were done to CMS HCC models to understand how these models compare, if there's any improved performance or gaps between the different models. I could take a stab at that one. So these initial models that we're releasing are concurrent models. And so what that essentially means is that we're using same year diagnoses and demographics to predict spend in the same year. And concurrent models typically have much higher predictive power and much higher eval. They score much higher on the eval metrics than CMS HCC, which is a prospective model, right? It uses previous year diagnoses to predict spend in the next year. We do plan on releasing prospective models soon, but these first initial models are concurrent models. And so, yeah, they have if you look at, we'll kind of walk through the documentation here in a bit, but they have a R-squared of around 0.5, which is going to be much higher than CMS HCC, which is like 0.1, and that's mainly due to it's not an apples to apples comparison in model types there.
Yeah.
Wyatt asks if the recommendation is to train your the models on your own data or to use the pre-trained models.
Yeah, I mean, you could choose to do both. So, but if you're training your models on your own data, you're basically benchmarking against yourself. So if you're performing really poorly, you're learning that behavior, and then you're predicting that you're performing just as expected. So, I mean, training predictive models, like Brett was saying, concurrent models it's different if you're trying to do a model to benchmark versus you're trying to do a model to predict how you're going to do next year. If you're trying to predict how you're going to do next year, it's a good idea to train the models on your own data and see how you're going to do next year. But for benchmarking purposes, it's better to train on a large population that's external to you, and then you're benchmarking against that. The whole point is to compare to some external population different than your own.
All right, these questions, they keep rolling in. As soon as we answer one, two more pop up. So Shivharam asks if these models are used to calculate risk-adjusted rates for readmission measures. So I can take a stab at that one. So we do have a model that predicts readmission rate. So it is of course risk adjusted via all of the kind of things that Coco was talking about, where we're adjusting for the demographics of your population, the sickness level, the geography, and things like that. I think is what that question is asking. Anything you'd add?
Yeah, you absolutely, using our readmission model, you can absolutely do a risk adjusted on your readmission rate.
And then last one for now, Tommy asks, how do you account for contracting differences between data used to train the model and data the model is applied to? Do they need to be apples to apples on a contract basis to produce meaningful insights?
Yeah, so the model is trained on a large population that obviously has all kinds of patients, and so the model's learning all those behaviors. And like I was saying, when you're making predictions on your population, you're making predictions on a patient by patient basis, and so it doesn't matter what the distribution looks like in your population. You're just making a prediction for each person based on how they look like. And if your population is just full of outliers, it doesn't matter. You're just making a prediction in each outlier. But the model was trained on a data set that has presumably seen people that look like the people in your data set. It's only a problem if the people in your data set look like nobody in the benchmarking population. But the whole idea is that basically the axiom that you're starting with is that there's going to be some patient that looks like the particular patient you're looking at in your data in the benchmarking population.
I think the one exception might be if there's some sort of a carve out or something, and what you're calculating as like total medical spend or something doesn't actually, like, that you're like missing claims that would naturally go into that because of some sort of carve out in your contract or something like that. That could impact things. There might be other examples too. I mean, VBC contracts are so tricky. But I know you guys have a lot more content to roll through, and I want to make sure we get to that. So let's pause on other questions and start going through again. And I think feel free to keep asking questions. We'll try and fit some more in. And then like previous meetups, if there's questions we don't get to, we'll follow up in Slack afterwards.
Sure. So I'll just go through this example of just basically showing you, if you wanted to train one model manually, what are the kinds of things you want to think about when you're doing this manually? And then I'll hand it over to Brad and show how we're basically doing this automatically for all the models at once. But for creating a readmissions predictive model, we have the goal of creating a model that can predict hospital readmissions. We start by inspecting hospital readmissions in your own data. So in the Tuva data model, there's a readmission smart. And in that readmission smart, there's a readmission summary table that looks like this. So that readmission summary table, it's out of the box in Tuva, and it has one row for each acute inpatient encounter in your data. And it only has encounters that have no serious data quality problems. So for example, if one of your encounters was missing a discharge date, it wouldn't be on this table because that encounter would be useless for training a model or for doing any readmission analytics. And these are examples of the kinds of fields you see in this table. We don't show all the fields because the table is very wide, but there's just examples of the columns in the table. You have things like the encounter ID for each encounter, the person ID, the admission date and discharge date, the length of stay, the DRG for the encounter, etc. This particular feature is very important. It's called the index admission flag. It's a binary flag. If it's 0, it means that the encounter does not qualify to have a readmission count against it. So for example, if the encounter has a discharge disposition indicating that the patient left against medical advice, that encounter would not be eligible to have a readmission count against it. If the index admission flag is equal to 1, the encounter does qualify to have a readmission count against it. So to train a readmissions model, you want only the rows with index admission flag from this table. And this column is the target. This is what we're trying to predict. It's a binary flag that indicates whether that encounter had a 30-day readmission or not. And so to create a data set to train the predictive model, you write the following query against the Tuva data model. And so notice that we're taking every row from the readmission summary table where index admission flag is equal to 1. And we're joining to the patient table so that we can grab sex and birth date and use that as inputs to the model. And so these are the features or inputs that we're using in our model. We're using sex, we're using age at admission, which we're computing ourselves. We're using the length of stay, the discharge disposition code for the encounter, the DRG code for the encounter. This is a diagnosis grouper for the primary diagnosis in the encounter, and a specialty cohort that the encounter belongs to. And then this is the target or the thing we're trying to predict, whether or not the encounter had a readmission. So the output of this query against the Tuva data model gives us the data set that we're going to use to train the predictive model. And the predictions will be at the acute and patient encounter grain. So for each encounter, the model is going to predict if it had a 30-day readmission or not. So this is the first thing you have to think about when creating a model. You have to figure out what is the training set that we're going to use for the model. In this case, for a readmissions model, it's pretty easy to create this if you're using the Tuva project because you already have a readmissions table. So you just write this query against that table. The output of that gives you a data set that you can use to train the model. So now let me jump into a Python environment where you can, this is the query that I was just showing you. If you write this query against your data model, you have the training data set for a readmissions model. And then you have to bring this data set, which I outputted to a CSV, into your Python environment. Here, I'm just bringing it into a pandas data frame. And then you have to do some data transformation to prepare this data set to train the model with. Here are examples of typical things you might look at. For example, if you have categorical columns, things like sex, discharge disposition code, DRG code, diagnosis, CCS, these are categorical columns with discrete string values. And the machine learning model doesn't deal with strings, it deals with numbers. So you have to convert these columns to numeric values. And so here's some code that would convert these columns to numeric values. There's different ways of doing this. In this case, I'm just assigning different integers to each categorical value. That's recommended when you're using tree-based models, but when you're using linear models, that's not recommended because it's taken as an ordinal feature, not as a categorical feature. There's other things that you might want to do, like scaling features that are numeric to make sure that they have you scale them so that they have a mean of 0 and a standard deviation of 1. This can help with model convergence. Then you want to split your data set into a training set and a test set so that you can train on the training set and then evaluate the performance of the model on the test set. Then you want to train your models. Here's just an example of training a random forest classifier and an XGBoost classifier model. Once you've trained the model, you want to evaluate the performance of the model. So here's some code to evaluate how the models are doing and reporting out standard performance metrics like precision and recall and F1 score for how the models are doing. And then finally, you might want to look at what are the important or most predictive features for each model. So for example, in the random forest model, you have the age of admission being an important feature for predictive power. For the XGBoost classifier, you have the discharge disposition code and the diagnosis CCS as being important predictive features. So you've trained a model, you've kind of evaluated what it looks like or what are important predictive features for this model. And then you have to export the model to a file. In this case here, I'm exporting the model to a pickled file that anybody can then just import into their environment and use to make predictions on their own data. But if you were doing this manually, you would basically go through steps that look like this. You would create a model object that then you can use to make predictions. And then you would have to figure out the ML ops workflow to use this model on your data set and make sure that you're taking your data and you're transforming it in exactly the way we transformed this data and then applying this model to your data to generate the predictions. So that's just a taste of how you would do this manually for one model. But now I'll hand it over to Brad so he can show you how we're doing it in bulk for all the models in the Tuva project.
Yeah, thanks, Coco. Let me share my screen. And let me share the right screen. Are you looking at VS Code here?
Yeah.
Yeah, okay. So here we've got VS Code in light mode. You know, I know there's like dozens of us out there that use light mode on VS Code. So cover your eyes if you need to. But what we're looking at today for this, so I want to walk through kind of a end-to-end of how you would run the predictive models using the MART that we've built in the Tuva project, as well as the models themselves. And then finally, how you can bring the predictions back into the Tuva project for analysis by other MARTs potentially, or for visualizing with some kind of prepared dashboards that we've built. So I'll be doing this walkthrough in the CMS synthetic connector. This is that CMS synthetic dataset is dataset that CMS published. I think it's roughly 10,000 members over 10 years. And this project, it's available on our GitHub. And what we're doing is we're just transforming the dataset into the input layer for the Tuva project to run. And inside the CMS synthetic connector, of course, we have the Tuva project, which is a package inside the connector. And in the latest version of the Tuva project, you might have seen there is a folder called benchmarks. And so I want to walk through kind of how this works and how this is set up a bit. Inside the benchmark folder, it's broken into two subfolders. One of them is pre-predict, one of them is post-predict. This pre-predict folder contains the models that will be used to run the actual prediction code on. So this does all of the transformations that Coco walked through to get the data ready to actually generate predictions on. We have two tables here. One of them is at the person year grain, so one row per person per year that has eligibility in our data set. And this is used to generate the PMPM type predictions or any of the predictions that require a denominator. So we are, as part of the 74 different models that we're releasing, we have models that predict overall PMPM, overall paid amount, and then we are predicting as separate models each of the encounter groups. So we predict inpatient spend, we predict outpatient, office-based, and other. And then we predict each of the encounter types. I think at last count there were 30 or so encounter types. And then in addition to predicting dollar paid amounts for each of those, we are also predicting encounter counts. So this allows you to calculate things like a PKPY, inpatient PKPY, ED PKPY, SNF PKPY. You can all do with these encounter count models as well. So this table transforms the data, and as you can see, it's a very wide table where we have columns for each of the features that are potentially used by the models. And I say potential because we have a lot of features in the prediction code. We've done feature selection, so not all of the, I think, 300 columns or so here actually get used. They're not all important or have any predictive power whatsoever. But they were potentially used by the model during training time. And then the other table in this pre-predict folder is called inpatient input, and this predicts at the acute inpatient grain. And so that walks through kind of the other thing that Coco demoed, which is how we're predicting length of stay, readmission rate, as well as discharge location. Those are all for each acute inpatient encounter in your data set. We're predicting what do we think the probability of a readmission would have been, right? Or where do we think this patient likely would have gone given the training set characteristics, or the characteristics seen in the training set. And these models are disabled by default. And so if you want to run them, the way that you do that is you just need to enable this benchmarks train variable. You can do that via, the command line. Ideally, if you're orchestrating this via prefect or airflow or something, then you can invoke that as you would normally. Here's the command that we can use. There's a tag as well to just run these models. So if we run just the benchmarks trained models, as well as setting the benchmarks trained variable to true, then that will run everything in this pre-predict folder. And let me actually just jump over to Snowflake so we can look at the output of that table. So here in Snowflake for the CMS synthetic data set, you can see here is the output of that table, where we have one row per person per year, as well as all of these feature flags that are potentially used by the model. Okay, so now that we've run the pre-predict models, now we're actually ready to run the prediction models themselves. And so this is done outside of DBT. This is Python code that we need to run. And so in the demo today, I'll be demoing this in a Snowflake notebook, which runs, if your environment is different, you just need some kind of Python environment where you're importing, basic Python libraries like XGBoost and scikit-learn in order to actually run these models. And so you'll want to jump over to to get the models themselves. They're hosted on the Tuva Project's Hugging Face page, where we have a repo that contain all the files needed to run. And the easiest way to get to that without going to the Hugging Face directly is just on the tuvaproject.com. Under docs, we've got a nice write-up of kind of all the different things we're talking about today, best practice and so on. But at the bottom, we do link over to our Hugging Face page. And that'll take you to our organization landing page. And at the bottom, we have the different bundles, the different grades that we're predicting for each of the models. And so in this example, we're going to walk through the PMPM model. That's found in the cost encounter repo on Hugging Face. And if you've never used a Hugging Face repo before, they're just like any other Git repo, where you can git clone and copy these files locally to your computer. And just a little walkthrough of the files that are in this repo, if you haven't seen these yet. The models themselves, like Coco described, which contain all the weights needed to run, as well as the scalars or any other things that's used to run predictions on, are located in this pickled bundle file. And so when you clone the repo, it'll clone locally, and you'll have that ready to go. In addition, we're also open sourcing the actual code that was used to train the models themselves. And so if you are really, for all the in-depth, in the weeds questions, and you're curious what decisions were made, how did we do any kind of feature selection, what kind of hyperparameterization tuning did we do, if you want to tweak it and you happen to have the LDS data set and you want to train the models themselves, or you want to do it differently, this code will give you everything you need to get started there.
Well, in fact, Brad, isn't it true that it doesn't have to be LDS data even, right? Like when we get access to commercial and Medicaid data, we'll effectively repurpose the same code to train, or is that not quite true?
That's true, yeah. Yep.
So if you have access to any data sets, you can plug them into the Tuva data model and run this code. Now, it may not be plug and play, because the characteristics of those data sets, could have various factors that make the the modeling decisions that we made for this data set kind of invalid, right? So you'd want to step through that. But from like a code standpoint, you should just be able to execute stuff.
And if you want to train the models on your own data for purposes different than benchmarking, for example, if you want to predict what your spend is going to be next year based on this year's spend, you might want to add features that we don't use, like I was describing, things that include your provider's utilization patterns. That would make the models more accurate.
Yep, absolutely. But for just, if all we're interested in is just running the models out of the box that are pre-trained, then we've provided this predict PMPM and encounters notebook here. And I'll jump over to that in a second. We can run that in our Snowflake environment. A couple of the other things that are in this repo that could be used, I think I did see a question come in about the different features that are used in the model. So we store kind of some metadata here with the feature importance that we've saved just for informational purposes. Detailed eval statistics for each of the targets that we're predicting, and then a feature fill rate table. And this is useful for like data quality debugging purposes. I found when predicting on a different data set, there were some issues with the benchmarks and they weren't quite working right. And so I calculated, feature fill rates for all of the features that were used to train the model, and then feature fill rates on the data set that we were predicting on. And it was quite obvious that we had 0 filled features for all of the CMS HCCs. So we had a data quality issue where CMS HCCs, which are features in the model, they weren't being calculated properly in our code, and it was due to we were missing a field in the eligibility table. So this can be helpful with debugging the predictions themselves. Okay, so for actually running the prediction code, I've got the Snowflake notebook here. These should be pretty much plug and play. Some kind of minor configuration that you might want to do is in this top section here, you can specify different output table names if you want to save it in a different database or change the name of the table that we're saving. And also, if you wanted to change the name of the output table that calculates the eval statistics on your data set, you can all do that in this configuration setting. And then the one hard prerequisite that you need to do is actually load this pickled bundle. So the way this notebook is configured right now is this is looking for it in a stage, in a Snowflake stage. And so however you normally load into a Snowflake stage, you would just want to add that before you run this code. And then if you did change the name, you could repoint it here with this variable. Other than that, it should be plug and play. So you can click run and you should see something similar to this. If everything was successfully saved predictions, you can see we're saving the predictions in this encounter predictions table. We're writing our eval statistics to another table, and then we are calculating those feature fill rates, like I mentioned, for kind of data quality debugging purposes. So let's jump over and see what those look like. So these were written to the encounter predictions table. This table, you'll notice, is at the same grain as was input into the model. So 1 row per person per year. But now instead of having columns for each of the features that were potentially used in the model, we have the predictions as columns. So here's our overall paid amount prediction. Here's predictions for each of the encounter groups. And then we'll have, the 30 or so some odd encounter types that we're predicting for, as well as encounter counts, like I mentioned, for calculating your PKPYs. Those will be all the columns that have count as a suffix appended to the name. And this CMS synthetic data set, while being free and great to use for some purposes, there is virtually no correlation between conditions that members have and spend on the claims. And so the predictions here are kind of, I think that R squared of like 0, right? So, so not great for actually demoing the predictive power of the models themselves. Okay, so if your goal was just to get predictions and have them in a table to use, then you're done, right? But the last step is in our pipeline is to then bring these predictions back into the Tuva project in DBT. So the way that we can do that is that's what these post-predict models are for, and we'll want to do a couple things first to be able to bring them back in. We need to add a sources.yaml if you don't have one already in your project, and point the sources.yaml to the output table where you wrote your predictions to bring those back in, and then add a variable to your dbt project.yaml that points to these sources because the models themselves reference the variables, and that kind of allows for some flexibility. And if you had saved them in another location, then you could just update the sources variable to point to that location, and it'll still get picked up by this post-predict section of the Tuva project. So these do kind of some minor transformations for data visualization, and we provide out of the box a Power BI that visualizes these expected values. And that's just to see what that looks like on my data set here. We've hosted it under the analytics section, under dashboards, and risk-adjusted benchmarks. So these are just pointed to the output of that post-predict folder tables. And here's what this looks like. So we're predicting overall PMPMs, and we're comparing that to actual for each of the year in our data set here. We have PMPMs for each of the encounter groups. And then here's some PKPYs. Like I said, we have 30 odd encounter types. I just brought 5 in here to for demo purposes. Some of the more common ones like acute inpatient or ED or SNF PKPYs are calculated. And then because these expected values are all brought in at the person year grain, we can slice and dice our population by any kind of grouping or sub cohort or attribution methodology that we want, and the expected values adjust accordingly. And so I've compared the I've brought in the chronic condition mark, which assigns each member to a chronic condition at the member level into this visualization. And so, for example, in this data set, members that have CKD, we could see they have an expected value of 2100 PMPM compared to actual of 2100, and those adjust accordingly, right? That's sort of the less expensive conditions you can see will also have a less expensive expected PMPM. And then similarly, we also have a page that kind of demos the acute inpatient metrics like length of stay, readmission rate, and discharge location, which is a multi-class classification algorithm. And because these are at the acute inpatient grain, we can then just join that to our core.encounter table and bring in any of the encounter fields to slice and dice this data by, such as the specific facility that the encounter occurred at, and our metrics all adjust by those dimensions. So if we wanted to know how our members are doing at this hospital compared to this other hospital, we're adjusting for the acuity of the visit and the acuity for the the specific conditions that those members have. And so length of stay, readmission, all adjust accordingly. And this, you can find this Power BI is open source as well. It's in the repo called Tuva Dashboards. If you want to clone this locally and kind of use it as a starting place to get started and just visualize the output of some of the models. Okay, so that was a lot, but that's end-to-end how you would run the expected values, generate expected values using the Tuva data model.
That's awesome. Thanks, Brad. Yeah, I think the ability to like slice and dice is like one of the best features of these the patient level risk adjusted benchmarks. Right? Because you can look at, it's like, how am I performing at an overall population level? But then if I want to like drill in and see, okay, where am I? Because there's probably patient populations where I'm performing less well. Where what are those, right? And I can literally weight those based on the volume of the patients in that cohort, right? So it helps me kind of hone in on opportunity. So I want to like come back to, we got 7 minutes left and we've had a few more questions and in the chat, and let's just try and run through those. Shivaram asks, and is that, oh, back to the risk adjusted readmission question. Does this align with CMS's risk adjusted readmission calculation? No, it doesn't. That is I don't know if this has changed in the last couple of years, but I used to know how this works and I've since forgotten it. But I previously, like, that wasn't something that was like reproducible. So like CMS's like targets that they set for the HRRP, hospital readmission reduction program, the risk adjustment that they do with that is like not like, my understanding is that that was not like reproducible by anyone other than CMS. I forget the particulars of that though. Ian asks, or it's just a comment, I guess. One particular area I've seen Medicare fee-for-service trained risk adjustment struggle is maternity-related measures. That makes sense. I would fully expect that to be the case. Good call out, Ian. Gordon asks, did you notice a relatively even distribution across the country within the sample, or was it skewed in any region? I could see the data getting pretty thin for certain categorizations and adding a lot of geographic bias. Pretty good question. I don't know, Coco or Brad, if you have any comments on that to share right now.
I didn't specifically look at the distribution across states, compare it to the whole, but we are including state as a feature in the model. So, and the idea behind that is you're adjusting for potential, regionality. With CMS, obviously, with a fixed fee schedule, that rates shouldn't be at play, but there is some payment adjustment with the CMS has some payment adjustment factors. So state is a feature in the model, I guess. Short answer.
Yeah. Sarah asks, similarly, is the first model presented accounting for regional, local demographics, same clinical profile of patient in Boston versus Indianapolis? I think it's the same answer, right, Brad?
In terms of geography, Brad, the only feature is state.
Yeah, that's the lowest level that's in the LDS data set. So yeah,
Makes sense.
We don't have zip code or anything to put in there.
Krishna asks, what's the ground truth used for measuring performance like F1 scores? I assume the answer to this is basically our train test split approach.
Yeah. So but there is no benchmark that you're comparing that to. You're just I don't know if I understand the question, but I think there's no ground truth. You're just training the model in a training set and then testing it on a test set. And if you get a particular number for an F score, you have nothing to compare that with. That is just what it was on your training set.
Okay, got it. It's just a split between training and test on the existing data set. Okay, got it.
Yeah.
Thanks.
Caleb asks, assuming quality data often leads to quality predictive models, are there additional data sources beyond CMS that you could reference or use to diversify your data set? Yeah, I think I'll add something here, and then if Coco, Brad, if you have anything to add, the answer is definitely yes, right? Like, and I think there's papers on this, right, where you can bring in like, clinical data from like, lab results for, certain like HbA1c, fasting glucose, LDL, different things. that make the data richer and allow you to create a more accurate model. I think the question is, like, if you bring in those features in the model that you train, they have to be there in the data sets that you apply the model to, right? And so if you train the data on a claims clinical data set, then the model is only useful on combined claims clinical data sets. And it can be, claims clinical, claims social determinants, claims, and most everybody has, but when it comes to value-based care, ACO type analytics, the common data that we all have access to is claims, right? And some people have other data sets. A lot of people do have other data sets, but it's not kind of the lowest common denominator. Coco, Brad, anything to add to that?
Yeah, no, I agree with that.
Claire asks, where do I see the features used for each model?
Yeah, so in those Hugging Face repos, we've got CSVs there that should have list of feature, and we have feature importance as well, ranked high to low, where you can see all the features in the model.
Jason asks, I've been trying to do some modeling like this, but all of my treatment population opted into the program. This means there's inherent selection bias. Have you found any approaches that account for populations that are at a particular moment of care? Jason, this is actually what I did my master's thesis on in economics. So happy to chat about this offline if there's interest. These models don't there's no kind of treatment effect taken into account in any of these models, but I think you can use the risk scores that are generated from these models as an input to those sort of program evaluation models. Also, another plug for Ian Duncan, his book that Coco mentioned, he's got a second book on program evaluation that if you're doing that sort of thing, that is probably worth checking out. Ian asks, have you explored reliability adjusting any measures yet, or strictly risk adjustment, right? Reliability adjusting. I'm not sure I follow. And we've only got probably less than a minute. So Ian, maybe follow up in Slack on that one. And then Kevin just says, thanks so much. And we're at time. Oh my gosh.
Wow,
Perfect.
we ended just on time.
You guys must have practiced. Okay. Well, this was great. Thanks so much, Coco and Brad.
Thanks, everybody. Happy
you
to
guys.
keep the conversation going on Slack with anybody who's interested. See you all.
Thanks.